Alright, welcome AP1. Today's Tuesday, March 24th. Alright, our goal today is to use the Kirchhoff's loop rules for our activity number 2. Of course, you should be up to date with all of the activities, as well as your 3-ring binder assignment. Eventually, probably sometime in May, you'll be able to turn that in for Q4, and I suppose we can double the score for Q4 because it will combine both Q3 and Q4 for 100 total points. That's huge. So make sure your 3-ring binders are up to date, so that you're ready to just turn them in for some credit and boost your grades. Alright, so if you haven't done it already, make sure you download the second activity, Advanced Circuits. It should look like this. So I swapped the 2 pages. The second page seems to be the easier one, so start with the second page and then go to the first page. Okay, so go to start with the second page, which is the simple one. I say simple, but it's actually called a complex circuit in that it's something that has both series and parallel elements. Of course, you can set up how you want to set up the resistors. We're going to use the same DC Circuit Kit from Phet to do this, and I changed the values a bit to 10, 33, and 56, and then we'll use a 30-volt battery instead. Okay, so make note of the changes to the values, and just update your file. And then open up the DC kit from Phet. Is anyone in chat? Can you guys hear me? Say something in chat so I know I'm not talking to myself. I can see a bunch of people. Oh, there we go. Okay, we're good to go. Stovetop, thank you very much. Alright, we'll go ahead and open up DC, the DC kit. Of course, DC, remember, is direct current. Basically, all it means for us is that the voltage supply, the power supply, is giving us a constant voltage at all times, whereas AC is sinusoidal. Z has ads on his streams. Oh yeah, by the way, we hit affiliate. Yeah, wireless high five to everyone. Let's go on Wi-Fi. We need a wireless high five emote. / wireless high five. Nope. So we need something like that. So we are now a Twitch affiliate. So I don't know what kind of benefits that is, but I think there's like a priority stream of some kind. So priority streams are up. I think you can do cheers and sound effects, but I don't actually know how to do those. But yeah, you can cheer and stuff, or I don't know, make like a sound on stream, and that'll get my attention. But anyway, we're on our way to becoming a partner, I suppose. I'll have to start streaming video games like a real Twitch streamer. Alright, so we want to build our complex circuit with 3 different resistors of 10, 30, and 56. So make sure you can take a note of the different values. So I've updated it to these values. Alright, so that was 10, 33, 56. Remember, you can click. Oh, these are wires. Whoops. I guess I'll keep the wires for now. Here are our resistors. Let's go and do it in diagram mode. So here's our resistor. 10, that's good to go. We'll make this one 33. 33. And we'll make this one 56. 56. Wow, you actually used it. How did you do that? How do you even... Oh well, whatever. Don't copy him. Let's go and build it. So here we are. Wires. Okay. Now of course mine looks slightly different from the actual diagram, but just focus on the current flow diagrams, not the electron flow. Now it doesn't actually matter if I'm starting from the bottom of this one or the top of this one. These two are basically connected. This is called a node. So this is essentially the same thing. Of course you can make it look like the diagram that we have by, let's see, by positioning them a little better. Positioning them like so. Oops. I don't think I can do that. Darn it. Oh, this is more work than I thought it would be. Here we are. Okay, now it looks exactly like our circuit. Again, it doesn't really matter because the bottom is just a node, and you can make contact whether you're up here or in the middle or down below. All 3 points are actually the same point in space, right? In regular space, obviously not, but in the electric field space, the other part of space, they are essentially the same point in that they have the same potential. Okay. Anonymous cheer. All right. So that's our first, and of course, use your multimeter. And oh, we didn't set our battery. Click on the battery, make it 30 volts. Whoa, too much. And of course, the animation speeds up a little bit. You can see how the little arrows are moving faster to indicate that there's a higher amount of current. Okay. All right. And recall that if you want to measure current, you need to make a break in your circuit. You have to break the circuit apart and insert your ammeter in between. Boom and boom. This will allow the current to flow through the ammeter and get you your values. Unfortunately, this ammeter only goes up to the hundredths place, not the thousandths place. Okay. When you do voltmeter, you just have to make contact at the top and bottom of the resistor. And if you do it backwards, it might give you a negative voltage. And that's okay. Just swap the probes. So, for example, if I put the red one in the front and then the black one at the back side here, we get negative voltage. But that's okay. The value is still the same. So you can always just take the absolute value and say that the voltage drop at resistor 1 is 9.5 volts. Remember, our battery is 30 volts. So we're only losing 9.75 at the front. That means whatever's left over must be at the other two. 20 and a quarter. 20 and a quarter. Notice how if I touch here in the middle, it's still 20 and a quarter. Because that's because all 3 points, top, middle, top, mid, and bot, are all 3 the same potential points, or have the same potential. Okay, and that's why those two are parallel. So we know that the oops, wrong one. We know that the first two, this one up top, the one down below, these two are parallel with each other. Once you combine them in parallel, then they are in series with the one in front. All right. Now for the slightly more complex circuit, just slightly more complex. This picture on the left is an actual real world diagram. Using our big kids circuit boards, we would build it like this. Unfortunately, we can't use our circuit boards, so we're going to go to the virtual world. And so we have a diagram, a schematic on the right. The first one is just to illustrate how you should wire it up with our big circuit boards. Alright, so in this one we have 5 resistors, and the 5th one being the one in the middle, going across from corner to corner. Alright, so let's analyze this circuit a little bit and then we'll be off to the races. Okay. So we have five resistors in the form of a diamond here. Yeah, this is similar to something called a Wheatstone bridge if you put an ammeter inside. So that's where we're going, but the reason why we have this is to see how circuits or diagrams can be neither parallel nor series. But when that happens, we rely on Kirchhoff's loop rules to simplify, or sorry, not simplify, to solve it. It's going to call this R1, R2, R3, R4. Okay, and it says to make sure that the resistors are not symmetric. Oops, we have double R4s again. Make sure they're not symmetric. So don't put like 10 and 10 across each other or anything like that. Just make sure they're randomized. So 10, 30, 56. That's okay, we can use another 10 here. 30. Something like that. Something that is not symmetric in any way. Okay. Now if I do the current flow diagram, it gets a little complex or complicated. We know that we should come out of the plus end, so we'll go out this way. And then we get to this first junction here, this split off. And so based on how the pathways are, some of the current will go this way, and some of the current will go this way. Okay. But now you get to another junction. Okay. This first current that's split off can either go down or to the right, and the second current that's split off could go up or to the right. And they'll try to do both. Okay, they'll try to do both. There'll be a beam struggle between, and the two forces will fight each other. The two flows will fight each other, and one flow will win out, resulting in the net direction. Okay. Typically, remember, current takes the path of least resistance, so the pathway that has the least amount of resistance will have current flowing through that way. Okay. So I'm just going to say that it is, it is downwards. And again, it is okay to assume at the start, once you do your loop rules, you solve for it. If I5 is a negative number, that means you were wrong, it was going the other way. But if I5 comes out as a positive number, then that means you are right, and everything is A-okay. Okay, so my current direction for R5 is an educated guess, I guess. It could be the other way too. Well, let's see. Why could it be the other way? Let's see. We have 10 here, and so more current wants to go through the 10. But once you get to here, there's a 10 and a 30 option. So more current will go through here instead of going downwards. So less is going down. Whereas over here, some of it did go through the 30, but now you have an option of going through the 56 or going through 30. So definitely some of it will take the 30 path and then go upstream instead, so that it can go through the 10 instead of the 56. So 30, 30, 10 versus 10, 10. So obviously 10, 10 is the best option. Going through the 10, going through the 10. But some of it will go through the 10, 30, 56 route. But that, that is a lot of resistance. It's like 96. So perhaps it's up. Using our simulator, we can actually see, and it will map out the current flow diagram. But if you don't know, then it's okay to just assume one way or the other. So it would be just as fine if we just said, oh, let's say it's upwards or something. Okay. Next, write down your loop rules. Remember, this is let's call this epsilon 1. Loop rules. What are my loops? Well, all the loops start off the same way and end the same way. It's just they run through the maze differently. There's one loop that is down R3, up R4. There is one loop that goes through R1 through R2. And let's do one more. We don't need that many, do we? Well, we might, because we have 5 unknowns. So, oops. Purple. Blue will be down 30, up up the R5, down the 10. Okay, we have 3 loop rules already. Now technically I need 5 equations. I can supplement our 5 equations with some junction rules. So let's go and write down. Let's start with red. So starting with red. So the red one is epsilon 1 minus I3R3 minus I4R4, and that's the end of the loop, so it must equal 0. Purple. Purple is the same way, starting with our battery, minus purple is thick. Let's go with a thinner point. Epsilon 1 minus I1 R1 I2 R2, and so after you go through the second one, we're done, so it should equal 0. Blue one's a little bit more complex. We have 3 things to worry about, so we start with the battery, of course, minus I3 R3. Okay, our viewer count has dropped a little bit. I am worried that people are kind of giving up or something. Keep going, keep going. Our AP test will be nice and easy. We're all going to get 5s this year, and I'm sure school will start again sometime after spring break, potentially May. Minus. Now, again, as long as your pathway direction and your current direction are the same way, you're always going to subtract your voltage drop from the resistors. Carry, very good. Carry, thanks for subbing, or sorry, following. Easy 5s. I'm still awake. I'm not a gamer. Carry the torch, lol. The torch, lol. Epsilon 1 minus I5 R5 minus I2 R2 is equal to 0. Is equal to 0. Alright, let's do some junction rules. Junction rules. We'll use, what should we use? Oh, let's use the Galaxy pen and do this junction here. Whoa, Galaxy pen. Alright, so at the first junction, ooh, that's kind of hard to see. At the first junction, we have some current, the total current. We'll call this I total. I don't like this at all. Let's just use black. So for the, I shouldn't say equal. For the first junction, we have the total current going in, and then I1 going upwards, and I3 going downwards. Okay, so our equation would be I total is equal to I1 plus I3. Okay, let's do another junction, and another junction, and another junction. Ooh, rainbow pen. Okay, rainbow. How is this any different? I don't know. Alright, for this one we have 2 and 4 going in, and then I total coming out. So I total is equal to I2 plus I4. Now those two are equal to I2, then 1 plus 3 must equal 2 plus 4. Ooh. Not in terms of math, I should say I1 plus I3 equals I2 plus I4. And let's do one more, because there's this I5 to worry about. What's this blue one? Ocean. Let's use the ocean. Alright, the ocean junction. We have I3 going in, I3 going in, and then we have I5 going up, and upwards to the right, I4. Okay, so I4 going upwards to the right, I5 going upwards, and I3 going in. So this means that I3 must equal I5 plus I4. Alright, we have so many equations, but having more is always better because we can always substitute, or at least make sure that the values that we're getting are correct. The way to check would be alright, I just asked the school if they can unban Twitch. Apparently no. They will not unban Twitch. Well, that's that. I just need to do like a restream or something that can stream to 2 different sources or platforms at once. Streamlabs only does Facebook and Twitch, or YouTube and Twitch. I can't do Twitch and YouTube apparently. That's really stupid. They don't want us to watch Ninja. Yeah, I guess. Well, you can't really the fact that you know about it obviously means that it is not working. You can't really stop by having a firewall. Firewalls don't really work. Anyway, I will refrain from giving my opinions. Let's go back to here. So you will set up your circuit and then make some measurements. After you make your measurements, you need to use Kirchhoff's loop rules. You need to use your Kirchhoff's loop rules to figure out what these values should be. So plug in the values, solve for one of the i's, kind of like what we did yesterday. And then once you solve for one, then you can go back and plug it in and solve for the rest. Subscribe. Wait, you can subscribe? Wow. We have one subscriber. Yikes. Did someone say ninja? No, we did not. Just subscribe to the YouTube thing. That's, I believe that's just a click of a button. Subscription on YouTube is like following on Twitch. We want to hit 100 subscriptions on YouTube. That'll give us a custom URL link that we can use. Whereas here we're already at 100 followers, so our YouTube numbers are bad. All right, we have 3 junction equations. We have 3 loop equations. That's already 6 equations, and I only have 5 unknowns. So if I have 6 equations for 5 unknowns, I should be A-OK. A-OK. Going back to our simulator now. Simulator, go and reset. We need to create, so how do we make it? Oops, what am I doing? Battery. Okay. It's kind of like a diamond, so oops, not a battery. I need resistors. 1, 2. Actually, I want to use wires. View. Alright, let's make this diamond thing. Oops, that's too big. Oh, I didn't use wires over there. That's alright. Wires. The wires will just give you some spacing, and it also allows you to connect the ammeter easily. Let's stretch this out a little bit. All right. And finally, we need to connect the corners to the battery. Conventional flow. Whoa, what happened? Okay, when it's symmetric, you'll see that the current does not flow through the middle, and this would give you 0 volts. Would I5 point inward or out of junction C on the diagram? Junction C? You mean the ocean? Again, I labeled each current at the start. No, it is the top one. Top one? Junction C. Oh. Let's get back. Yes, junction C. There we go. That's the one. would I5 point inward or out of junction C? Based on our diagram, it is going into C. So what is going into C? If you look at the arrows, 5 is going in, 1 is going in, and 2 comes out. Meaning I5, so this is junction C, I5 plus I1 equals I2. At least based on how we drew the arrows initially. Again, you can just arbitrarily pick the direction of the arrows. You just write your equations, you solve for your variables. Now, if your current comes out negative, that means you chose wrong. And it is the opposite direction instead. Okay. So again, because the values of my resistors are all the same, it is symmetric, this will give us zero current flowing through. So we don't want them to be symmetric. What do we say? 10, 30, 30, 56. Again, you can make your own or copy mine. 56. This one was also 10. So 10, 10. This is 30. Okay, so a little bit of current. So now it looks like it's downwards. So that means when you solve this problem, you're going to get a negative current for I5, and that negative current will tell you that you chose the wrong direction. We had it right the first time. Oh, wait a minute. Wait just a minute. Take a look at the direction of the battery. I don't think I have that correct. If I go here, do I have it correct? Yeah. If you take a look at this diagram here on the top right, of course our battery symbol looks weird. Remember, that's the EMF symbol, electromotive force, or it could be that it's two batteries in series. If you see this big line, small line, big line, small line, yes, this is an ideal battery, a perfect battery called electromotive force or EMF. Or you could look at it as two batteries that are side by side or linked up, kind of like your remote for your Amazon, what is it? Fire Stick or whatever. I think Fire Stick uses batteries that are lined up like this. Ooh, this is terrible drawing. Let's try again. So here's our cylinder. Here's a little dimple. Here's our cylinder. Here's a little dimple. And these two batteries are touching end to end. So you could also view it this way as well in your mind. Positive is left. Why is the current moving? No. Yeah, positive is left. So if I go back to our simulator now, we have to reorient the battery's direction. So let's go and cut this off. Okay. If you look at it in diagram mode, you'll see how the big line is on the right. So that's the dimple part of the battery. We need to make sure that the big line is on the left side. Ah, now it's working. Very good, Slazer. Slazer 360 gets it. You can click the battery and it has a button to rotate it. There, that one. Ooh. Or do it manually like I did instead of using the button. Okay, so to make measurements, again, you would have to make breaks. It doesn't matter if you break it in front or behind. Oh, looks like it's stretched out. Ooh, I like this. And be careful because it's only going to give you one sig fig here. So take the values with a grain of salt. Use P equals IV. Don't use the other power equations. Use P equals IV for power. Okay. If I want to use voltmeter, look, there's some voltage dropped because there's current flowing through. Oops, I did it backwards. We want the black one to pick up. Now, negative is okay, actually. Negative means that you're dropping that many volts. It doesn't really matter how you want to look at it. As long as you know that the resistor is going to drop the voltage, it's going to use up the electrical potential energy of the electrons. It doesn't use up the electrons. The electrons still move through. It just takes away the electrical potential energy from the electron, converting it into heat. Resistors get hot when they use up the electrical potential energy. Okay. Now, if these are light bulbs, we should talk about light bulbs a little bit more. Lights, or old-fashioned lights. Light bulbs. Did we already do this? I can't remember. But anyway, light bulbs are non-ohmic. Which means does not follow Ohm's law, or do not. So light bulbs do not follow Ohm's law per se. I mean, it sometimes does. Recall that Ohm's law is V equals IR. That's because cold bulbs have a very low resistance. Okay. Whereas as soon as you turn it on, and when you get hotter, or when it does get hotter, it will increase its resistance to its actual value. So hot bulbs have high resistance. Okay. So essentially, when the light is turned off, it is cold, therefore it's low resistance. And as soon as you turn it on, you send a bunch of current through. Because the resistance is low, current is going to be high. So the moment you turn on a switch, you're actually sending lots of current through your light bulb. And this is why sometimes light bulbs, blow out at the start. They don't just blow out after being used, because once it gets hot, the resistance picks up. That means the current that is actually flowing through the bulb is decreased. So it's once when it works well. But sometimes from a cold winter day, you turn on a light bulb, the resistor inside is cold, therefore lots of current passes through it really quickly. This will melt the wire and break the connection so the light bulb does not turn on anymore. Okay. All right. So you don't want to use you don't want to use an ohm meter to measure the resistance of a light bulb, especially when it's off, because that's going to give you a different value. So for light bulbs, don't use an ohm meter. Okay, what you would do is use a voltmeter. You would measure V and use an ammeter to measure I. And by doing V divided by I, you'll get R when it's hot. When the light bulb is hot. Okay. LEDs are different. LEDs. Anyone know what LEDs are? Or anyone know what this acronym stands for? Please type in chat now. LED. Light emitting diode. Bubble guy gets it. Bubble guy gets it. Light emitting diode. So this thing has a symbol with an arrow and a line. So this is the symbol for an LED, not a light bulb. The arrow tells you which way the current can flow, and the line tells you that if you go the other way, it's going to block it. LEDs only work in one direction. One direction, meaning current must flow to the right if you orient it this way. And if current tries to go the other way, it won't. It'll block it and the light won't turn on. You know what else has diodes? Full bridge. Yeah, subscribe to Electro Boom for more circuit wackiness. That guy's a genius. LEDs work in one direction. Okay. Now, when you have an LED, you'll see that it's a little tiny thing here. It has a long tail and a short tail. And usually the long tail is the positive end and the short tail is the minus end. Big positive, big positive. Okay. All right. Whereas traditional bulbs are bi-directional, they can work both ways. So light bulbs work both ways. Okay, so that's all we needed to know. If you have any mastering physics questions, you can ask them now. We can go over mastering physics. Otherwise, you need to finish off your activity here, activity number 2. Okay. Alright, chat, if you have any questions, ask now. I will be here for some Q&A session right now. Let's see, mastering physics. Okay, so the next one is due in 4 days. This is more on circuits, or not really on circuits, but more on current and stuff. The next one is definitely on circuits. Let's see, most of you got 100%, 99. Wow, very good. The most missed question was question number 2, the circuit construction kit, Ohm's law, and power. We have 79% on that one. Actually, number 4. The most missed question was number 4. It says a 100-watt light bulb is brighter than a 60-watt light bulb when both operate at the same voltage of 120 volts. If instead they were both operated at the same current of 0.5 amps, which would be brighter? Select the correct answer and explanation. Yeah. So number 4 was the most missed question. For the second circuit of activity 2, do we use the same 10, 30, 56? Yes, keep the numbers the same. The battery should be 30 volts, 30 V, and do it the same way. Yep. Now, of course, you're going to have to choose 5 resistors, so up to you. You can choose which one you want. if you want to use 256s or 230s, 210s, as long as you use all three, and then the other two you can choose to double up. Just make sure they don't crisscross and make a pattern or anything like that. One way to check, of course, would be to put it on the simulator and just make sure there is current flowing through the middle resistor. So as long as the middle resistor is not 0, it is fine. It should work. All right, I'm going to go over question number 4. So it says a 100-watt bulb is brighter than a 60-watt bulb when they both operate at the same voltage of 120. So we have 100 watts, which is power, at 120 volts. This 120 volts is special in that this is what we get out of our outlets, the stuff that's on the walls. It's 120 volts. Technically, it's AC, but it just means that the current goes back and forth between the light bulb. But no matter which way it's flowing, it's still going to work because it's going to still heat up the resistor. Resistors are also bidirectional. Whereas for LEDs, you can't just send the AC current; it won't work. AC current does not work for LEDs. So what do LEDs require? Well, it requires a converter, an AC to DC converter. That's what the adapter plug is for. And you can convert your AC into DC, and then it sends the DC through the LED, and that should light up the LED. Anyway, at 100 watts, we have 120 volts. This gives us how much resistance? Well, if remember P is equal to IV, of course, but it's also equal to I squared R, and V squared over R. There we go. Okay, so using this third one, we can say that the resistance is equal to V squared over P, which gives us 120 squared over 100 watts. All right, so what is 120 squared over 100 watts? 120 squared divided by 100. This gives us 144. Chat, are you with us? Go and do it on your own. $144 ohms. So that's what the light bulb is. Doing the same thing with the other one. You get 60 watts at 120 volts. This gives us 144,000 divided by 60 now, 60 watts, which is 240. So of course the second light bulb has much more resistance. Okay, so if I use the same current, which one will be brighter? So the idea behind this question, remember, you're supposed to ask yourself, why did I give you this question, not just solve it. The idea why, or the reason, is to see that we can use different power equations to serve us at different places or different problems, to whichever equation is best suited to answer the question. Here we have the same current, and it's a question about power. We know what the resistances are, so why not use number 2? Power is equal to I squared R, and if the current is the same, then the power must be proportional to the resistance. Okay, so whichever has the higher resistance will give you the most power, and so the 240 ohm resistor or bulb would be brighter. All right, we are dwindling with our numbers, so I'm going to go ahead and stop the stream here. Thank you for watching. I'll see you next time.